Good afternoon, everyone. Over the past 3 years or so, our group at NITK Surathkal has been working very closely with the IBM's Linux Technology Center in Bangalore in India to build into gem5, into the gem5 architecture simulator models of the power processor. And this talk, I'm going to focus on the journey and on what we have done so far and what are the capabilities of the simulator because of this collaboration. I'm Basavaraj Talawar. I'm a faculty at the National Institute of Technology, Karnataka. And so what gem5 is? Gem5 is currently the de facto architecture, system architecture simulator used heavily in the computer architecture field. So basically, there are processor models and there are system core and uncore models. So there is processor architecture that there are multiple processor models that allow us to plug in the required processor model and to simulate the processor at a given level of detail. Similarly, there are a bunch of I/O models and memory subsystem models so that we can plug in the required details and then build our own system and simulate the full system. So so basically gem5 allows there are existing all components for processors, for the memory subsystem, the I/O subsystem, and some of the interconnect, and one can rig up a system of a particular configuration and execute workloads either as a full system mode or in the system emulation mode. Gem5, the name itself, the origins of Gem5, there were two simulators in the past. M5 was a detailed processor and I/O model simulator from the University of Michigan. GEMS was the was a fairly detailed memory hierarchy simulator. So the combination of both of these simulators is Gem5. Right. So what Gem5 provides is there are a rich set of CPU models that simulate the processor at different design points, starting from a simple functional simulator up to the completely out of order simulator with all the components required to do out of order simulation. That's one thing. There are memory models for all the levels of the hierarchy, for SRAMs and DRAMs, and even now very recently the NVMs and so on. And so the memory hierarchy also includes some of the consistency and the coherence protocols modeling. It also allows that. The I/O models, there are a set of I/O models for byte based and block based and network I/O and so on. Two modes of simulation are possible in Gem5. The full system mode, where all the components, all the layers and all the components can be simulated. A complete operating system can be run on when we are running in a full system simulation mode. A system call emulation mode is more of a restricted environment, and we would always like to simulate and we would always like to gather characteristics or metrics while running in the full system simulation mode. What is shown in the small table is actually there are 4 kinds of CPU models, starting from the atomic simple to the timing simple, which is a functional simulator with a minimum number of timing information associated with it, an in-order pipelined CPU, and a completely out of order CPU, and basically the range of trade-off is also sort of shown, that the simple functional simulation will take very less time but will be least accurate, whereas we are running in out of order mode. The simulation will take much longer, but we get more accurate results, right? So why this journey began is Gem5, I already mentioned, is popular in the computer architecture circles for all the processors shown in the first column, right? So there has been support for the others. Some of the others have been consistently worked upon. People are committing threads or committing models into the other processors. For example, ARM has a strong continuous support. RISC-V is gathering a lot of momentum, whereas the power, and x86 also enables full system simulation. So importantly, ARM x86, what is not shown here is the AMD. The AMD models are also mature. The AMD models can also run full system simulation. Now, the status of the power, as you can see, is sort of highlighted that there is no maintainer, and the power support was pre-2005, which is ISA version 2.06, and at the time it was 32-bit big endian, and it could only run system emulation mode and simple programs. So we took up this task that we will bring up to speed to today's ISA version, and we'll try and run full system simulation on the power model. That was the task that we set out to complete. Right. Of course, the gem5 software itself, the simulator itself, is distributed with the generous BSD license, so we were able to do that. And gem5 is pretty much every architecture conference, and most of the papers use gem5. It's now more or less considered as the standard for computer architecture simulation. This is in the academia. In the industry, two companies heavily use, I believe, to some extent Intel also uses. AMD heavily uses gem5 internally, is what we've heard. Also, they have published all of their gem5, not all of, they've published some of the more prominent models upstream into gem5, and they have announced all of these changes in those several conferences. Of course, the specific model that is in AMD's expertise or in AMD's family is the APU. So the APU modeling is cycle accurate in gem5, and you can also see the total number of commits is large and a slightly dated number. Similarly, ARM's gone one step ahead. They have what is packaged as a research starter kit to enable ARM affiliated research worldwide. So you download that research kit, and it's basically a 64-bit ARM V8 model. And again, full system simulation can be run on it. It also contains a GPU model, and ARM is one of the more more active in the gem5 in the gem5 code stream. So status of power before we began the project is shown in the top box. The old ISA version 2.06 32-bit big endian programs we were able to run with an inner restricted environment, no full system simulation support, and newer tool chains were not working. So what we planned is by the end of the so as soon as possible, right, try and simulate programs in ISA 3.0 and try and get 64-bit little endian programs. That's what ISA 3.0 contains, and try and get full system simulation support. If these three were done correctly, then we should be able to run the Linux kernel. Right? That was our target when we began this project. And what the mode of engagement was our group at NITK Surathkal, and with a strong mentoring and with strong collaboration with the IBM LTC in Bangalore, we set out with this target. And first of all, people would not know where my institute is. So if you know Bangalore, and that's on the right hand side, right? That's Bangalore in the underlined. So that's where Bangalore is, and we are on the west coast, approximately 250 miles as the crow file, 250 miles, right, to the west of Bangalore. And there are a couple of pictures of my institute. I just wanted to sort of show that. So the mode of engagement was most of the time the group worked in the university at the university, and some say 6 months or so on and off they also spent in IBM Bangalore. So we are looking to expand this collaboration, and we are now trying to seek out more groups that can participate in this gem5 effort. So I start off talking about the phases of development. The first thing we wanted to do was to support integer instructions, little-endian 64-bit integer instructions. These are the group members that were involved in this, and what we did was take the Linux kernel that was compiled in the 64-bit little-endian PowerPC compiler, and extracted out all the instructions that the Linux kernel uses. So that was the list of instructions that had to be implemented first of all in the gem5. How gem5 enables implementing these instructions is it has an internal DSL that we can describe the functionality. We can also basically for a given major opcode and a minor opcode, and the mnemonic write out the functionality in the DSL. That's the specific code. That's the specific program in which the description had to be written. This was one of the earlier instructions that we added. The specific example that we are showing here is parity word and parity double word. Of course, the arrows point out to the timeline that we started off in May 2017. By May 2017, starting from early June 2017, we were able to, early January 2017, we had to go through a lot of code base and to figure out where it is to be added and what's to be done. And we were in a few months able to figure out exactly where modifications had to be done in gem5. The gem5 code base is sort of fairly convoluted, sort of fairly large. And so, and what is shown in the code itself is a couple of instructions: the parity word and the parity double word, and the functionality that is required with the input operands and the functionality that has to be coded into the model or has to be modeled into gem5. We began with this, and there were a large number of instructions. There were a few instructions that we added in. It included loads and stores and the whole family of loads and stores, and a fairly large number of arithmetic instructions and the logic instructions. So arithmetic instructions included addition, subtraction, multiplication, division, and its offshoots, all of them, and of course also the modulo. With the logical instructions, we had all the logical instructions and separately compare, family, count the number of ones, parity, family, then the branches and the shifts and rotate. So all of these instructions had to be written in. Once we had done that, we had also to enable support for ELF ABI second version. With the pre-2005-2006 was ABI v1. This had to be updated also, so the little bit of code was added into gem5 to enable support for ELF ABI v2. Once we had done this much, we had all the components in to run simple assembly code which used only these bunch of instructions. So that was phase one. So this itself took some amount of time. So once we'd done this much, then we thought, okay, now there are a bunch of instructions that we can run. So we'll put together a full system and try and run, we'll put together a full system and see what we can do with it. And we started off rigging up one system, and this fairly simple system just contains one processor and a memory. It's connected through a memory bus. So what is being shown here is the configuration file, and we sort of modified the configuration file, put total number of CPUs equal to 1 and the address range that we wanted to simulate. Right, and we didn't do anything else. So just absolutely simple full system, or a simple system at this point. Once we added that, then we had to add all the special registers that are required to keep context while the instructions are executing inside the processor. All the special registers, the counter, the exception register, the floating point status, machine status register, importantly, etc. So all of that had to be added. SRR0, SRR1, the entire sequence of special registers we added in, and we declared all of them, and we also sort of wrote that they can be used in the input operands, what will be the code names, and so on. All of that we put in, and after that, the instructions that were required was to return from interrupt. So both hypervisor return from interrupt and the return from interrupt RFID instructions were added in. Right, and what is being shown is, of course, the functionality of these instructions, which how does the MSR get updated when the RFID instructions and HRFID instructions are executed. Then we were ready to add in the decrementer interrupt support for, of course, the goal being the final Linux kernel is going to execute on this. For the kernel to have any kind of timeout and context switch or any sort of sense of time, then we need the decrementer interrupt. So we put in the decrementer interrupt first. The couple of instructions that are highlighted there are the PC is being stored into the SRR0, and finally the PC state is 0x900, that is where the decrementer interrupt handling happens. So we were now at this point we were gaining expertise on, or we were gaining knowledge on how to include interrupt handling and how to simulate interrupts and into gem5. So once we were once that much was done, the only thing that was remaining to execute a bare metal program was to set up the memory system. So at this point we didn't have address translation yet. So also, as you can see in the code, we're not actually translating any address at this point. The virtual address is equal to the physical address. That's something that we do next. But if we just put in a placeholder for address translation here, no translation is being done. But given this much, with the return from interrupt instruction, and with the decrementer interrupt, and with the placeholder for the with no translation, right? Physical address is equal to virtual address. We were able to run bare metal programs at this point. So or what is called the real mode programs, right? And so that was again an important milestone. So what was missing here was, of course, the address translation, which is what we took up next. And POWER9 uses the Radix page tables, and that was something we had to put in. So a sequence of figuring out how this has to be done, and we put in extensive documentation inside the code to show how the Radix page table works, and how does the page table walk actually happen inside the code. At this point, again, we were not ready to handle faults. So what actually was done was there was always a hit in the page table. The walk was always successful. So there was no fault at this point. So we had taken care of that. The fault handling is what was missing. So we added the fault handling next. So that's we are entering into the third year now. We are entering so the exception handling and the fault handling was added next. So the fault handling was required to do system calls in the first place, and that was one of the things that was primarily required. So the first initial interrupts that we supported was the program interrupt and the data interrupt, and the interrupt that happens while memory is being accessed either in the instruction cache or in the data cache. What is shown on the left hand side, and on the right hand side is the asynchronous program interrupt that happens while in the middle of the execution of an instruction. So if there is a decrementer interrupt, for example, then what has to be done is the current instruction completes and the next instruction will begin to execute when the RFID returns. So that's why this instruction address +4 on the right hand side, whereas in the data storage interrupt the fault or the interrupt has occurred. The interrupt has occurred while the instruction is being executed, so the same instruction has to be repeated. So that's those things we put in. Once the exception handling support was added in, so we were able to trap instructions, and we were now ready to service page faults. And with all of these put in, we were now more or less ready to execute the Linux kernel. And so first of all, to even do that, we had to modify the compiled Linux kernel, because the Linux by default assumes that there are multiple processors. So some of those constants had to be turned off. Some of the multiprocessor code portions that assume multiprocessor context had to be changed either to unique processor context or had to be sort of commented out. Those things we did, because at this point we didn't have doorbell interrupts to be able to simulate multiple process SMP. We didn't have that capability. So as you can see, what the arrow points to is the total number of active CPUs is equal to 1. So those are some of the changes we had to do in the Linux kernel itself. And then we were able to run the Linux kernel. we were able to begin executing the Linux kernel. There were a few errors while we were doing that. There were a bunch of errors in the implementations of the previous instructions, and we fixed that. There were a few instructions that we had not come across before, but was required. For example, the clear block of cache or put zeros into a block of cache is what is shown in the bottom left, and some error correction that we had done for the move to MSR and such instructions that we had encountered with errors. We did that, and once we had crossed that point, we came to a point where we had to get the kernel log sniffing. So currently, at this point, we are only able to look at gem5's output. We are not sniffing into kernel's log. And what we did to sniff out kernel log is to find out where print k actually writes into the buffer, or what is the address into the buffer the print k writes into, and then found out through gem5 assembly or gem5 binary object dump we did, and then found out the exact instruction addresses that use this, and find out where the buffer's addresses are, and basically read that out, did a mem copy, and then read it out, and then that's what the output is shown on the right hand side is the kernel log. We sort of probed into the gem5 to get out the kernel log, and we also set up GDB. GDB works well with the other processor models. So there was already some sort of infrastructure that hooks onto the GDB inside gem5. So some hack was needed, and the GDB was plugged in, and we were able to interface with GDB also. So at this point, so we had both GDB and the kernel log printing out, but it was also useful to get a serial console in. Again, gem5 has all of these infrastructure already into it. 8250 UART was already there, and that what was required was to create a new device, and we call it G500, and that was configured to read out into the serial console, and we were able to get a serial console. With the serial console, you were able to telnet into the gem5 device, and we were able to look at the kernel logs again. So once that was done, so we were able to run the full Linux kernel at this point, and the next step we did was to try and put the firmware on it. So that's the OpenPOWER OPAL, OpenPOWER abstraction layer. So one of the advantages with putting OPAL was that the device tree, or the device tree construction OPAL would do for the kernel, and also there are other scheduling and interrupt handling capabilities that OPAL provides, which we could use later. So so that's why OPAL would have been was a good component to put in. So we again, OPAL had to modify it a little bit to make it understand that it was running on gem5 and not on an original processor, to make it understand that it was running on a single processor simulation mode. So there were a few tweaks to be done on OPAL. So once that was done, again, OPAL was also running correctly. So the OPAL built in the device tree, and that device tree was handed over to the Linux kernel, and the Linux kernel would boot inside gem5 correctly after that. So this was an important milestone again. This is what we had set out to do early. So this happened in April, it's a few months ago, and what is shown is the full execution of gem5 in the pictures here. After that, so at this point, Linux is running on a Uni-Processor in Power 64-bit little-endian. So a few changes we had done originally to the Linux kernel to make the kernel assume that the underlying processor is a Uni-processor. So we had to undo all the changes to make it, to try and support SMT2, SMT equals 2, that is. So we turned off all of the config SMP made false, and total number of CPUs equals 1. So we turned off all of those in the Linux kernel. And one of the interrupts that was required to simulate simultaneous multiprocessors was the doorbell interrupt, and we put in the doorbell instruction and support for the doorbell interrupt also. Importantly, we had added the atomic instructions. So at this point, we were able to run the SMP kernel, and yeah, we undid all the changes that we done to the Linux kernel and a few hacks. So now we are able to run simultaneous threads in CPU 0 and CPU 1, and of course there was some timing and waiting to wake up the second CPU. The first CPU wakes up the second CPU, the first thread wakes up the second CPU, and so on. But we were able to run SMT simultaneously, and this is a snapshot for that. So at this point, yeah, so OPAL node, yeah, so all of this was running correctly, and now a unmodified OPAL runs correctly on the Linux kernel, correctly runs with the Linux kernel on gem5 on a SMT equals 2 PowerPC now processor. Currently, we are working on the external interrupt handling, and so with the external interrupt handling, we are yeah, so we are putting this code in. I think we are at this stage now. So the next sequence of steps that we are planning to do is the processor model that is currently running is is a timing simple processor model. We are now the next stage is to put in a pipeline, first of all an in-order processor, and the next stage after that, if once we are successful with the in-order pipeline processor, we will be moving on to the out-of-order fully pipeline processor. We have to add in some of the register renaming and the TLBs and you know, scoreboards kind of equivalents there. So that's the next step for this processor for the project. All of the code that we've been working on is on GitHub now, and it's under the family power-gem5. The modified gem5 code that runs that contains the PowerPC models is in the first link. The second link is the OPAL firmware that is again modified for this gem5, and the Linux kernel version that works with this gem5. So all of these are now uploaded, and we're also in the process of upstreaming all of this into the original gem5 project. So yeah, so we are in that process, and yeah, so that was what I had for now, and a fairly large number of students from our group have been involved, and one half of them are currently at IBM also. And also a very strong support from IBM. The first row is, I have to call out Madhavan, Anju, and Gautam. They are the ones who drove the mentoring from the IBM side throughout the project. Of course, the bottom three, or the second row, three guys are all students, who are currently working with IBM LTC in Bangalore. Based on their experience in the gem5 project, they were all sort of included into. So that was a good win for them, and it was great for us also. Yeah, this slide doesn't have the Dipankar Sharma, who was the seed idea for this, but that's I have to mention Dipankar also here. So yeah, so we're only beginning to see a lot of possibilities. Again, I'm talking to people here, and they're saying, where is this feature and others, and so there are a bunch of components that we still have to work on. The core and the uncore, I think. So it's an exciting journey, and we hope that more people will come on board. We are looking for more universities and more groups to sort of work with us together to sort of build a full system simulation model, and the vision is sort of a very it's a slightly large one. So it will require multiple groups and multiple people to be working together on this. So that's all I had. Thank you for the time. Yeah. Thank you guys.
So do you, what kind of I/O devices? Do you have anything simulated as well?
The I/O models are all there. Specifically for the power system, we have not seen anything. We've not gone there yet. But there are a bunch of IO models that are both generic and, for example, any other system, the x86 systems, and so they all have IO models. We haven't tinkered with any of these IO models yet, but they're all there. And in the simulation, they're all in the simulation. So yeah.
For one of your long-term goals, would it be to actually simulate an open power-based system?
That is the goal. Yes, that's what we are after. We want to do that.
Okay. And most of them will have two systems, right? The host and then the VMC.
Right.
Do you do anything with the VMC stuff?
So we have not gone to that point, so I can't comment. But the idea really is, the holy grail really is to be able to simulate all of the components correctly. The OPAL was one of the in that line, so we put in OPAL first.
Yeah, that's a good step.
So so all of the stuff that we are looking at, right? So OMI, OpenCAPI. So we don't. There are so many things. Much later, but we are not still at that point. But that's something that we want. So if somebody else can.
When you actually create a simulation of the system before you build that hardware, that board.
Yes.
We do that at IBM all the time.
Yes.
Use gem5.
Yes.
I talk to the guys that they know about it and stuff.
Yes. It would be too early to say that we'll replace what you have, but it'll be so much easier when you have your own open source simulator that you're free to use and modify, and also the academy is also working on this gem5. So that's where the value comes in for the simulator. Sorry.
Contributing back to the gem5 main upstream project, those changes.
Yes.
And they have been accepting and receptive so far.
So they have been, first of all, surprised, because after 2005 there has not been a maintainer. There is so the core group in gem5.
In 2005 probably wasn't anyone from IBM either. So probably PowerMac or something, right?
So that I think that person Andreas somebody. So he's is not a part of gem5 anymore. So they don't have the power expertise. So they are coming back to us asking us to validate and everything. So that's happening right now. That conversation is going on. But that's been happening since 2 months or odd now. But it wasn't accepted immediately because they aren't also not sure what has to be done, what's correct, and how it is to be validated. But that process is going on. Yes.
I apologize. You are with the university.
I'm a faculty at the university. Yes.
You're a professor there.
Yes. I'm a professor. Yeah.
Are you granting scholarships for the students to work on this, or just part of their academic?
It's a part of their curriculum, and so usually, so all the students were master students, and it was their final 1-year project. We have 10-11 month final year project. So when we said they work both at the university and at IBM, so the mode is they're working on gem5 at the university for the first 6 months or so. After that, they could probably go to IBM for another 6 months. And when they go to IBM, they get, of course, internship. There's otherwise also they have scholarship as part of their master's course. So that is anyways there.
But IBM is not paying for those scholarships themselves.
Not when they are in the university. When they go to IBM's as interns, usually they go as EB interns, for example. Yes. Yeah. But the mode of engagement is remote calls and Skype and that kind of thing. Every week, that sort of thing has been happening. Yeah.
You have how many students doing that today?
This now there is one. There's one only.
Okay.
So usually it's just 2 per year. It's been 3 years now. 2 per year. Yeah. So if there aren't any more, thank you very much. Thank you. So.